All right, so no questions, I guess? That's amazing. That's surprising. Okay. So last time we got through section 14.4, believe it or not. Yeah. If you were here, you know what I'm talking about? Mentally and physically. 14.4 is about tangent planes. And the really funny thing about Math 180, for example, it's the same, just as funny with Math 281. They make it sound as if linear approximations are something different from tangent planes. Like in 180, once you find the equation of the tangent line, that is the linear approximation of the damn thing. They should just put them together. I love this book for that reason. Tangent planes are linear approximations to a surface near some point. So, of course, before we got into this, because what gets built into the equation of a tangent plane at some point, the tangent line to a point is dependent on what? How do you find the tangent line? Going back to Math 180. How do you find the tangent line at a point on a curve? Slope. Yeah, you need a slope, which is derivative, and the point, and then you're basically there. So here, you can't say the derivative anymore, right? In Math 180, in 2D, strictly 2D with x and y, and that's it. You could say the derivative because it's the only way you can go. We assume that going forward in the positive x direction is it. So the derivative makes sense. It makes sense to say that. Are you guys with me? Now, if you were here last time, you understand you can't say that anymore. The derivative looking which way now, right? So if I'm on the mountain, I just drop from a plane and I grab onto a mountain. I'm like, oh shit, I can go this way and go flat. It's just a little path. This way is straight up. This way is straight down. I think I'm probably going to go this way. You with me? So it depends on which way I'm looking. My slope this way is basically 0. Oh, nice slope path. This way it's basically almost infinity. Shit, no. I just dropped out of a plane. I was probably kind of tired and freaked out. This way is straight down. You guys with me? So now that we have all these different directions for inputs to go in, it depends totally on the direction I'm looking to talk about the derivative. So you can't say the derivative, be done with it. You've got to say the derivative in the direction of the x-axis, which would be what as in notation?
Partial derivative?
Yeah, fx. I like it. Which you could also denote as freaky d f.
Partial. We call it d also?
Yeah, I would call it d, but it's partial. You don't want to say partial f respect to x. I like it. You don't really see or hear d by dx anymore, really, with these partials. Right? You can call it freaky d if you want to. See what your next teacher thinks of that. Or you could alternately see this as d, partial d, partial x of z, right? Because normally z is equal to f of x, y. Are you guys remembering from last time? Okay, I like it. As similarly for fy. Okay, I like it. And now, hopefully, you guys realize something we're going to extend to here a little bit from now, but it makes sense right now. Is what if I had a function of, 3 variables? Then I can have fx, fy, of z. Function of 3 variables does not necessarily mean. Now what is this? Let me slow down. So this guy here is built on this. How many dimensions is this living in specifically? 3. So this guy.
4.
Yeah. Now, they don't have to be 4 physical dimensions. Remember what I said, like it could be a heat map. So it could be a 3D room, and you could walk through like Minority Report. Minority Report? We're almost to that. We can test shit. You walk through it, and at every point in space might have a slightly different color related to the heat or related to whatever the color would mean. Right? You could have a color related to wind chill, to air pressure, to whatever. So color very often is a 4th dimension for us on graphs. Like it doesn't have to be a 4th physical dimension because that gets really, really, really freaky. a fourth physical dimension. The shit would that be? Well, so sometimes that could be time, but that's really kind of not easy to capture either visually. Okay. So what's the equation of? So if I have a surface defined like this, what is the equation of the tangent plane? At, let's say, x naught, y naught, z naught.
Z minus z naught
Yeah, z minus z naught.
equal
Fx.
fx.
Is it f of x now?
No. This means the derivative of that f with respect to x, treating y as a constant. I like it. And then you evaluate it at a point. I like it.
Close.
Times.
Oh, x minus x naught.
Yeah. So, and then we're going to add another piece. But recall, real quick before I finish that out. I'm not done with that yet, right? But recall, this looks very much like y minus y1 equals m times x minus x1. That's basically what the hell this is so far, right? Output equals slope times input stuff, right? But of course, I got a whole other piece to it because I have a whole other input. X and y are both inputs, right? So I'm going to have fy times y minus y naught. So that's what we talked about yesterday. You could add this sucker over and call this L, and that would be the linear approximation. Nothing amazing there, really. Yeah, let me stop there for a second. All right, is everybody cool with you guys remember this? All right, okay. So now I'm saying instead of just x and y, we have z that's dependent on x and y. So it's the exact same idea, the exact same format, but now I'm including a whole other direction in which to go.
So the f subscript x is not your slope?
This is definitely my slope, of course. Yeah, just like m was my slope, this is my slope in the x direction, this is my slope in the y direction.
Okay.
So what does the outputs do? They start at x naught, y naught, z naught. So they start at z naught, right? And how much do they change by? Well, it's got to be based on how far you go away from x naught times its slope. Plus the contribution to how far you go in the y direction times its slope. Let me let that sink in. So why does this really, if I replace this with what we know it actually is now, f prime, remember back in the day, we could say that. So I'll be f prime at x1. Is that cool? We used to be able to use prime notation, not so much anymore. There's too much shit going on for that now. So why does this make sense? Because f prime is change in y divided by change in x. Why can't we do that kind of thing anymore? It's related to why we have to use these symbols now. I can't make simple ratios out of changes anymore. That's why this is just a part of it. So this is kind of like the complete picture. This is all the parts at once. The part that's related to how much the output changes because of how much I moved in the x direction. So if I move in the x direction a little bit, then my height could change. Depends on the slope in the direction I just moved. Are you guys with me? All right, so basically if the slope is 1, and I took a step over, I would estimate that the change in height should be a change of 1. Right? But I got to add in, if instead of just going that way, or instead of just going that way, I actually go some diagonal. I change x and y by a little bit. Now the actual resultant change in my height is going to be a combination of the change due to my x piece and the change due to my y piece. We see that happening in this equation. Okay. And again, it's kind of nifty that we can explain this formula in a different physical context than what we actually use to derive this formula. So if you go back to how we derived the formula, it's a little bit of a different way to go about it. It sort of is related to the way we look at it right now, but not exactly. But now I can interpret this in that beautiful combination of the x changing a little bit and also the y changing a little bit. So then the overall change in my height is based on both of those changes. I like it. Maybe, maybe.
Just to make sure, it's a change in x and y, right? I mean, you said that it's x changes and y changes. So that's the equation if it x and y change.
How much will z change? Yeah, exactly.
Yeah, but if you put something constant, then just one part.
Yeah, exactly. If I don't let y change from y naught, then this piece is going to go away. And then, of course, it only depends on how much it changes in the x direction.
So it becomes two-dimensional.
Exactly. And then it becomes exactly this, just with, different letters, but the same exact formula. I like it. Maybe.
And still partial derivative.
Yeah, still partial. I like it. So when do we need this? We need partial derivative symbol when the function I'm taking the derivative of have different options for what to take it with respect to. Let's say that again. So back in 180, we only had, even when we did parametric stuff, you only had the option of t. T was the only real variable there, right? Okay, I like it. So, and of course, when we were back in 180, we only had y as a function of x. So the only possible thing you take the derivative with respect to was x, right? And they could also turn around and say x is a function of y. It's the same damn thing I just said. X and y are just dummy variables. Who cares what letters you use? But now, I can't write total of f with respect to, I can't write df dx, because there's a whole other thing I could take it with respect to. This is only part of the picture, hence that's why this is called partial fraction, partial differentiation, right? So let's try a problem now. Let's get an equation of a tangent plane to some point. I like it. Randy's like, God, give me an application.
Show me numbers.
Show it. All right. Let's keep the Jerry Maguire shit to a minimum. Let's see. All right, let's take one right here. Oh, that looks yummy. Let's do this one. Ooh, that looks really gross. I like it. So given this here, I'm really curious what this looks like. Alright, so find the equation of the tangent plane to that surface at that point.
Yep.
So all you got to do is change your perspective a little bit. If I said find the equation of the tangent line to you in 180, you think I got to find the slope. And I got the point already. Okay, now you got to think, I've got to find the slopes in the x and y, right? And then you plug in the points. I mean, it's almost the same work, just a little more work because I've got a whole other dimension I can move in my inputs. That's perfect. Do that. Just to make sure everybody's on the right track. Well, what would you call, what is f of xy here?
X.
Yeah, this here.
X plus y.
X sine x plus y. So we're just calling z f of xy like we called y f of x. Not a huge deal. That's why this could be seen as df dx, when partial f partial x, or partial z partial x. They're the same thing. that derivative at the point. Yeah. Just like you do back in 180.
Yeah, okay.
So now we got two inputs instead of one. Now, obviously, if you have any trouble with derivatives at all, you're going to suck at this stuff. But hopefully, I heard from a lot of people, oh, it's just derivatives. Okay, that's good. That's the way you should look at it. You should say that. You should be able to say it, no problem. It's just derivatives. Who gives a shit? Love this while you can, because in our future, double and triple integrals. Yeah. So enjoy this while you can. So what's going to be involved with fx?
Product.
Product. I like it. So derivative of that guy is easy. Times this guy. Plus
Cosine x plus y.
this cosine. And the inside's linear in x, so that's going to be just a 1 for the no chain rule necessary. I like it. Fy is not going to be product.
X cosine.
Yeah, x cosine x plus y. And now to use the formula, you have to know the slopes, if you want to call them that. To know the partials, both partials at that input point of negative 1, 1. That's all, right? You just got to plug this stuff in. You just got to see what the slopes are at that point. So this, what's fx at negative 1, 1?
Negative 1.
Yeah, this would be negative 1 plus 1. That's 0, right? Sine is 0. Plus, and this would be negative 1 times cosine of 0. Negative 1, I like it. And fy at negative 1, 1.
Negative 1.
Same reasoning, right? In fact, notice it's kind of funky, but that happens sometimes. So we get negative 1, I like it. That's beautiful, thank God, right? I know some of you guys are concerned when we saw the trig in there, but if you don't know zeros, sine is 0, cosine is 0, I'm sure. So what do we get? We get z, let's put all this stuff together. Z minus 0 equals negative 1 times x minus, good, minus negative 1 plus 1, minus 1 times y minus 1. So we get z equals, let's see, negative x minus y, negative 1 plus 1, gone. That's crazy. So let's test this out. What does this mean? What's another way of looking at it? This is the tangent plane to this surface at this point. This is the plane that acts the most like this surface does at this point or around that point, which means it is a linear approximation. And why do we call it linear? It's not a line, but why do we call it linear? Because all the powers are 1. That's what we call linear functions. All the variables have power 1. And actually, it extends beyond that sometimes, but oh well, let's just stick with that for right now. So this is a linear approximation to this surface. So if I said, okay, what's the value of this function at, what is f of negative 1.03, comma, 0.96? So instead of using this shit, right, I'm just going to use this shit. That's a lot easier, huh? You guys see, that's the value of finding these linear approximations. And of course, you could figure out, I don't know if you guys remember, you get a linear approximation in 180, and you know, like, your tolerance levels and how far you can go away from the input. So if you built it around 0, how far can you go? Or even thinking about Taylor polynomials even. If you guys remember those? Yeah, maybe not. If you build it around a point and you could only go so far away from it in order for it to still converge and all that kind of business. Same idea here. I went a little bit away from negative 1, a little bit away from 1, so this should still work pretty well with this approximation. This, of course, gives me
0.006.
Yeah, so it'll be 1.03 minus 0.96, so 0.07. And can somebody, what do you get when you actually just plug that into this in your calculator?
Should be close.
Should be close. Should be. It's not good enough for us, though. We might have done this whole thing so wrong. You never know.
That calculator's on our customer.
Make sure your calculator's in what mode?
Damn it.
Wait. Radians, shit, yeah. Because you have, now watch, you guys should know this, but whenever you have something that's acting like an inside of a trig function and it's a multiplier somewhere on the outside, it's got to be in radians because degrees are made up shit. Of course, you get down to it, everything's made up shit, but at least radians is an actual measurement of the circle, whereas degrees is just something we just chose at random. 360 is a nice number. I don't know if you guys realize that we totally out of nowhere. An alien didn't come down and say, use 360. Oh shit, yeah. And we said 360 can be cut in a lot of different ways. Let's use that, yeah. So let's see. All right, let me see what you get. So you get, where'd it go? What'd you get? Times sine of 0.07, basically. Where'd it go? Yeah, negative 1.03 plus 0.96. Yeah, I get 0.072, which for normal humans would be about 0.07, would be good, right? Engineers, maybe, depends on what you're doing, that might not be good enough, but that depends on your error tolerance, right? It's a whole other aspect of this. How far away can you go? And remember when we were talking about the disk, when I said the neighborhood around something? So you have this point, negative 1, 1, in the xy plane, and there's a certain disk. It depends on your error tolerance, how far away you can go from that and still be allowed to use this estimation. Depends on how accurate you have to be. If you could be within 0.5, holy crap, man, you can probably get pretty far away from it, right? And it also depends on how weird the freaking surface is near that point. You could have something like, oh, it's so nice, and then you get really far away, or you have like, holy shit, you know, and then you can only go this far away. You guys understand what's happening? All right. Okay. Blah 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 blah. Oh, okay, perfect. So please do not. When they say find the linear approximation, you just do the same work you did to find the tangent plane, because that's all it is. That's all it is. Okay. And just real quick, I was talking about, I changed the input x by a little bit, I changed the input y by a little bit, so of course the output is going to be a combination of the results of both of those changes, which is why the formula makes so much sense. It's the x contribution plus the y contribution. Of course it is. Please let that make sense. Or don't to them, right? All right. So let me put this back up here at the top here. Here's my tangent plane formula. Let me put it in quick little form here. Let's see if you guys realize this. This is kind of like a gross change. I don't know if you guys have ever heard it put like that. A gross change could be, I could start at 3 and go to 5. That's a gross change. But I could actually replace each of these with infinitesimal changes and get, where was this at? The total differential, page 972. Yeah. Yes?
Did you forget something on that formula, the x naught, y naught?
Oh yeah, I just wrote it real quick. Please let that go. Okay, thank you. So obviously these have to be evaluated at the point when you're constructing this tangent plane. This is a more general idea. This is not tied to a point. This is, and notice what's sort of familiar, possibly. You guys should be used to this. If I said u is 2x, what's du dx? 2. Now, of course, we didn't do that shit when we were doing integration. You did substitution, right? You did du equals 2 dx, right? So see the similarity here. So this is not just, that would be just this piece, of course. And now we're adding in the other contribution in the y direction. I like it. So this is what's called the total differential. And now you see, and I can't remember if I put this up here yet or not. Because now you can really see why we call them partial derivatives, because each one of them is just a part of the total differential. Maybe. All right. So if I knew, let's see. If I knew how much something changed by here, I could estimate how much this changes. Right? If I knew the slight difference in the x and y direction on something, there's a problem in the book about a can and how much metal there must be given the thickness of the top and the sides. Have fun with that one. It's not that horrible, but you have to start with a function and then take the total differential of it, really, so that you can actually see the contributions from all the. You could change the r and you can change the h. So both of those have to come into play. That's going to be how what affects the total volume is going to be how much the r changes if it does, and how much the height changes, the radius and the height. You have to take both into account. I like it. So it would be a total differential of that volume formula. Okay. This is the general idea of a total differential. Now watch this. This is where things get interesting. And you're all like, this is where things get. We're moving into chain rule with partial differentiation. I know chain rule is like one of your favorite rules from Math 180. And now we're going to use it with this new partial differentiation. But I want you to notice something. This is kind of nifty. I don't know if you guys remember if your teacher ever showed you when you started doing parametric stuff, that you can actually just do this kind of stuff, right? In general formula. So here, what's really kind of nifty is the formula, if I had z as a function of x and y, and, let me just build this up for you, and x itself is some function of t, and y is some function of t. Cool, I like it. So I still have to use partial differentiation because what can I take the derivative of f with respect to x or y? Right? So if I want to get a total differential, so if I want dz dt, I want to take the derivative of z with respect to t. It's going to be df dx dx dt. Be really clear on which one's the weird d's and which one's the normal d's. Yes, sir?
So that the x dt would you just be solely doing the derivative of h of t?
Totally, exactly. I
I
love
wouldn't
it.
even worry about y. Y doesn't, because y is not even n, that h.
We're going to do a nice concrete example here in a second. Plus, so why is this still partial here? Because what can I do f with respect to x or y? Why is this a normal d? Because x is only a function of t. There's no options. So that itself would be the total differential of x with respect to t. That's it. That's all you can do with it. All right, maybe. So plus what? Well, df dy, dy dt. So partial f of x, dx dt, partial f of y, dy dt. And it doesn't exactly work like this, but it almost always works like this, except for real weird functions. This and this go away, and you can see how they both make df dt together. There's two ways to do dz dt. You can do df dt with the x's, df dt with the y's. Okay, maybe. So see the similarity between what a total differential is. And then you really just divide everything by dt, and it becomes derivative with respect to t of some chain rule kind of function, some function of functions. All right, so let's try an example. By the way, I slipped into 14.5 right there. All right, here we go. So let's say we're given Find dz dt. So that's exactly using this. Everything's the same exact letters, right? That's exactly using this setup. Now, I mean, technically, you could throw this in there and throw this in there, but you see how it's actually easier to keep them separate since you know the general rule of how it works? Gotcha. Especially when we start adding more letters in and adding more, Russian nesting dolls in there. Holy shit. You want to use the general idea and not plug stuff in and plug stuff in. Oh my God, the formula gets so disgusting. So do this. Let's see here. We should know by this little piece here is F, right? So just notice something. This piece here, it's just your regular fx, right? This piece here is just your regular fy. These are the parts related to the fact that there's another level of sub-variable in there, right? Okay, maybe. So what's partial f with respect to x? Yeah, plus 3y squared. I like it because y is a constant. It just comes from the right. Times, what's dx dt? Yeah, 2 cosine 2t. I like it. Yeah, and then plus, what's the partial of f with respect to y? Good? 6xy, cool. Yeah, so times dy dt, it's just going to be negative sine t. It's crazy. And now you just, distribute, see, then nothing's really going to go together. Poor little guys. Nobody's going to be really turns in. You clean it up a little bit. Do you guys like that? I mean, again, if you needed to, you could do each one of these separately and then just slam them all together and get the answer. Boom. But what's really important is knowing how to start this first step off. If they use different letters, right? They have some W's and some S's and U's, V's and A's and B's. What really matters is the format of this. Whatever the question is, dz dt, you have to be able to find that here and that here. Do you guys see the idea? And you have to split it up as many ways as there is to split it up. Why were there only two things here? Because there's only two ways to split that up directly. Okay, so let's go to the next level. What's the next level, Jeff? Well, the next level is if x and y are functions of s and t. Why? Because we can. And because it happens in real life, believe it or not. I mean, we should be very aware. Like if you wanted to go into like real meteorology, where you were the one writing the software for the supercomputers to chomp on to make predictions, right? And they'd be wrong almost all the time. Getting less and less wrong all the time. That's their slogan. Getting less and less wrong all the time. Sorry, it's a lot of work. You should realize there's going to be a buttload of variables that's going to be involved, and there's going to be how are the changes in one affected by the changes in something else. I mean, there's going to be a lot of freaking calculus in that. That's insanity. And some models ignore some variables and other models don't, and then they take the average of all those models, which almost makes for certain that it's going to be wrong. You ever looked at, I know we live in California, but you ever seen the path of a hurricane? Path of a hurricane. You guys ever notice that? And it's got that black line down the middle, and it's got the cone of uncertainty. I love that. It sounds like a get smart kind of thing. The cone of silence. Cone of uncertainty that opens up. So in about 5 days, it could be anywhere from there, or 500 miles over this way. Oh, thanks for that. But it's not their fault. It's like there's just too many freaking variables. And all the models disagree, and sometimes they disagree wildly. Right? Anyway. So, improving the formulas behind that software is a huge need. Oh, okay. So what about this? So what if we have, let me keep myself straight here. What if we have z is a function of x and y? X is a function of, what do I want to say here? Yeah, I can just do this. G, S, T. Y is a function of S and T. I like it. Now, let me ask you, what kind of question could I ask you to find the derivative? What kind of question? Before it was very straightforward. I could only ask you one real question, the partial with respect to t, right? Because t was sort of like the innermost only variable, really. It was controlling everything, right? So here we have two controllers. So therefore, I could ask you, now to be honest, I could ask you this kind of thing. I could say, what's dz dx? I could just ask you that. Is that going to involve s or t in any way? No, it's not. Because I'm not asking for, do you guys see that? What was the one I just asked you about earlier? I should have kept it up here. When I gave you z as a function of x and y, x is a function of t, y is a function of t, dz dt, didn't I? So of course it involved t. Shit, yeah. So please, now watch. I want you to realize we're going to write this down in the process of this, and I'll show you what I mean. So I could ask you easier questions that don't go all the way down to the innermost variable. So you want to identify when it's an easy question, obviously, and not do too much freaking work. So if I ask you, what's dz ds? It's almost the exact same thing that we had up here earlier. So remember, in this situation, it was I put f here, df dx, dx dt, plus df dy. I'm just saying d real quick for this. You guys, okay. All right, stay with me. Now watch. It's almost going to be the exact same thing, because I still only have two here, so it's going to be df dx. Let's say partial f partial x, and then what's going to go here? And not the d though, right? Let's be very let's not do like Jeff. Let's be very specific about how we say things. It's going to have to be a partial. Why the shit, Jeff? Why the shit? Because how many options are there for x to take the derivative with respect to? Oh shit! So if you only do one of them, it's a partial. So notation is important, even though I have people that it didn't change my answer. I don't care. At this level, you have to understand the notation itself is important. And understanding why the notation changes, it's what's going to help you keep track of when to do that. So why did I put a partial here and not there? Because here there's only one option. Here there's two. So that's got to be a partial. Plus partial f, partial y, partial s. So what would dz dt be?
All that.
Same thing, just with t's instead of s's, right? I like it. All right.
Is there gonna come a point where you're gonna ask for partial Z over partial S and Z?
No. But we can work up to the total differential here, right? But it gets a little weird when we have this third tier of things. You see, like this third tier of variable, right? So I could ask, well, how does the Z change if I change both S and T, right? Yeah, and then we can actually, what would, no, let's not go there yet. That's for later. All right, so now watch. What do you think is going to happen if I have this? So just make sure everybody understands. I didn't write this down, but dt would be the same stuff, just with t's there and there, right? Is that cool? Same stuff, just with t's there. I like it. So what if, instead of just this, I have w as a function of x, y, and z? X is a function of, I can just keep going with this here, right? X, let's say, is a function of u and v. Why not? Just to change things up. Y is also a function of u and v. And z is also a function of u and v. Just use k just because. And before I get too far away, what is this also, what could you use here instead? Instead of df, you could just use d. Partial of no, I for the whole thing, but I know you could have done this the same way, right? In fact, in a way, this makes a little more sense, to be honest, because then you can see dz ds, dz ds, dz ds, right? So together they make a whole partial z, partial y. So remember, I was asking you, I could ask you this question by itself. Does it involve any subparts to it? Well, no, because it itself is a subpart of this whole thing. So I could ask you this question by itself. It's a direct answer, right? I like it. So before we do this, let's hold on to this. Let's try an example of this one, right? Let's see if I can do this. So let's say z equals, well, it doesn't really matter, Jeff. Let me take one out of here. Where do you got some weird stuff? Book. Ooh, that's gross. Oh, that's coming up in a second. That's right. Here you go. I like it. That's not too bad. I like it. So what if I said find partial of z with respect to y and partial of z with respect to t? So do those two for that setup here. Where are you at? What time? Oh yeah.